And then, thank you for coming to today's technical workshop session in this very cold weather. Thank you for coming. Let's start the title, Progress of Softbank Network with Sensing Technology. We are Tak Saito from Softbank and Shiro Ryu from Meiji University. This is today's agenda. Introduction, challenges of WDM system, a solution with optical delay interferometer, and future plan. At first, I explain about collaboration with SoftBank and Meiji University. 8 years ago, collaboration with SoftBank and Meiji University has started. We have built a win-win relationship. SoftBank can be involved in cutting-edge research in optical transmission, such as analyzing technique of transmission characteristics duration. And the other hand, Meiji University can study phenomena that occurs in living networks. Now we introduce ourselves. I'm Tak Saito from SoftBank Corporation. From 2006 till 2021, I was working as a WDM system engineer. And from 2021, I'm working as network engineer at SoftBank.
Hello, I'm Shiro Ryu. I have been working at telecommunication company, KDD, and Japan Telecom and SoftBank. Now, in 2016, I moved to Meiji University. I'm now serving as a professor at Meiji University.
Now let's start the introduction. A large number of AI data centers are being built throughout Japan. There are data centers that can operate a large number of servers equipped with high-performance GPUs. According to a survey, there are 32 AI data centers, including those that are planned. Due to this situation, computational demand is increasing explosively. And this graph shows the growth of computational demand. In 2030, computational demand will reach 1,960 exaflops, so that a power receiving capacity of 4.2 gigawatt will be required. This is equivalent to 6 large thermal power plants. It is a very large amount of power. Regarding the location of data centers, data processing and power consumption are currently concentrated in urban area. Tokyo and Osaka area alone account for 90% of the entire country. There are problems such as power shortages, the impact of disasters, and delays. To solve this, it is necessary to distribute data processing and power consumption to local areas. We SoftBank announced a plan to build a distributed computing platform. This platform has a hierarchical structure of core brain data center in Hokkaido, Tokyo, Osaka, and Kitakyushu, a regional brain data center in prefectures, and sub-regional brain data centers in major cities. Distributed computing is realized by the data centers according to the role of each hierarchy. And communication occurs between each data centers. In particular, there is a large amount of traffic between the core brain data centers. The backbone network transports such large traffic. I will explain the backbone network in detail after the next slide. This is basic structure of a backbone network. Several backbone routers are installed all over Japan. Here, the WDM system is responsible for carrying the router's traffic. WDM is abbreviation for wavelength division multiplexing. It can multiplex wavelengths of different colors and carry large amounts of traffic. WDM systems are composed of ROADMs and ILS. In ROADM, As client signals such as 100 gigabit Ethernet are added or dropped. In the transponder, here, inside the ROADM, client signals are converted into transport signals. And ILA is an abbreviation for inline amplifier. ILAs are inserted the middle of transmission path and amplifies the attenuated signal. And next, move to challenges of WDM system. WDM contributes to evolve in order to carry the ever-increasing amount of traffic. This graph shows the history of WDM capacity. The line rate per wavelength is increasing year by year, like this blue line. The capacity of the entire system is also increasing year by year, like this green line. And next, I will explain how WDM achieves such large capacity. At first, light has X and Y polarization, like this picture. By carrying independent information in X and Y polarization, the line rate is doubled. In both optical transmission and wireless transmission, digitally modulated signal points are expressed on a two-dimensional complex plane. This is called a constellation diagram. Like this picture, X polarization and Y polarization are represented as independent constellation diagrams. Next, I will explain how to calculate the line rate of the transmission signals. The line rate is calculated by multiplying symbol rate, modulation order, and polarization multiplicity. Here, polarization multiplicity is fixed to 2. As shown in this table, line rate is increased by symbol rate and modulation order increases. Next, channels decreased by large symbol rate. The line rate can increase by the symbol rate, but it causes problems. The optical band that can be used for transmission is limited. As shown in this figure, as the symbol rate increases, each channel occupies a large bandwidth, which in turn reduces the number of channels. There are two problems. As the right figure shows image of path pattern, the vertical direction means wavelength, and the horizontal direction means ROADM location. By reducing channels, the number of path pattern decrease. For example, in this figure, the section between B and C is sold out. And another problem is that the growth of system capacity will be saturated in the future. As shown in the left figure, even if the capacity per channel is increasing, the system capacity will not increase. As explained in the previous slide, the symbol rate should not be increased. Then we want to increase the line rate by increasing the modulation order. As shown in this figure, the modulation order corresponds to the number of points in the constellation diagram. However, when the modulation order increases, the transponder becomes sensitive to phase noise. In this figure, the yellow part represents the signal point when phase noise is added. When the modulation order increases, the points get closer together, so it is necessary to reduce the phase noise. Phase noise sensing is important to know the source of phase noise. This is the first point of today's presentation. Earlier, I mentioned that light is composed of X and Y polarization. The state of polarization is called SOP. Light signal has SOP. When the optical fiber vibrates, the SOP changes. The transponder can compensate the SOP fluctuation to some extent, but there is a limit to its tolerance. Previously, we have observed the large SOP fluctuation over 1,000 500 radian per millisecond at a location in Japan, it is not easy to be compensated in the high line rate, especially in the high line rate. Next, I explain optimization of SOP tolerance. As shown in the left figures, the cost per bit, the tolerance to SOP fluctuation is increases by reducing the line rate. However, as shown in the right graph, the cost per bit increases by reducing the line rate. In other words, there is a trade-off. Sensing technology of SOP fluctuation is important for optimal network design. This is the second point of today's presentation. Next, power consumption of WDM. As shown in the leftmost graph, the power consumption per bit is decreasing by year. This is due to the evolution of semiconductors. However, the line rate is increasing year by year. So, as the middle graph shows, the power consumption per wavelength has recently started to increase again. And as shown in the rightmost graph, the power consumption per system is also increasing. Even if semiconductors evolve, we must pay attention to power consumption yet. Next, I explain the basic structure of transponder. The left figure shows the basic configuration of transponder. It is consisted of coherent DSP and several devices. The right figure shows the power consumption of each component of the coherent transceiver. The coherent DSP has many functions, so it consumes a large power like this. Next, let's take a look inside the DSP. The DSP consists of several function blocks. The adaptive equalizer compensates for PMD, PDL, SOP fluctuation, etc. And the right figure shows the power consumption of each block of DSP. Equalizer is the second largest power consumer in signal processing, like this figure. At the last of this chapter, I explain about the adaptive equalizer. The adaptive equalizer is generally composed of a 2x2 butterfly FIR filter. And the 2x2 butterfly filter has many tap coefficients. New coefficients is calculated by the tap adaptation algorithm and reflected in the FIR filter. This is repeated in real time. This updating cycle can be tuned by a parameter. And as the right graph shows, increasing the updating speed, the tolerance to SOP fluctuation is increased, but also increases the power consumption. This is the third point of today's presentation. Here is a summary so far. Phase noise sensing is important to know the source of phase noise. Sensing technology of SOP fluctuation is important for optimal network design, and adaptive equalizer consumes large power. Its updating speed should be optimized. Now let's move to the solution with optical delay interferometer.
Okay, now I'll talk about recent research results from collaboration between SoftBank and Meiji University. As Mr. Saito mentioned, phase noise is a very important parameter which determines system performance. So measuring the phase noise is quite important. Of course, digital signal processor of a coherent receiver can measure the phase noise using this equation. So the phase difference between this one, tau means one symbol time. So phase noise for during one symbol time determines the system performance. Of course, it's possible by commercially available technology, but it consumes much power. For example, for 200 gigabit per second systems, about 40 watt power consumption. To solve the power consumption problem, we developed a new technology. This is a photonic technology. This is delay interferometer. This is a block diagram with a Michelson interferometer that is very well known in the research area. Simplified diagrams here. Uh, Light is divided by this half mirror, and part of the light is going to pass 1, and part of the light goes to pass 2. So we intentionally make pass 2 lengths longer than path 1. And the length difference corresponds to the one symbol time. So after combining again these two lights and received by this optical receiver, we can measure the optical phase noise as I stated in the previous slide. So this technology uses fully optical circuits. So power consumption is very low. In this laboratory experiment, we have confirmed that power consumption was only 2.4 watt. So very much power consumption reduction is expected. And by this technology, we measured the optical phase noise. This is a histogram of the optical phase, and the black one is actually measured optical phase noise, and the red one is a Gaussian fit. And as you can see from this measurement result, this technology can measure the optical phase noise correctly. And also, you see this is a spectrum of this phase noise, and as is well known in the optical field, optical phase noise of semiconductor lasers is very flat, and we have confirmed also these characteristics. And in this case, delay time between pass A and pass 1 and pass 2 is set at 40 picoseconds. And also, we have discovered that such an optical delay interferometer can also measure the state of polarization as well as optical phase noise, as I stated. And output current of the balanced receiver after the delay interferometer is composed of IPNT, this is a phase noise, and IPOLT, this is a polarization component we have discovered first in the world. And of course, to measure the state of polarization, well-known technology, we have already a well-known technology. This is a result by using the polarimeter. This is commercially available. And this is a plane curve sphere, which shows a state of polarization on this sphere. But we also measured by delay interferometer the state of polarization. The results becomes like this. In this case, very fast polarization fluctuation, about 140 kilohertz, by using a fiber stretcher, which applied external stress to the fiber at very high speed. And you can see conventional technology that polarization fluctuates like this. But using new technology, we can also measure polarization changes like this. But from this histogram, we don't know the phase noise amount of phase noise. But we have also developed the digital signal processing to extract the phase noise from this results. This is the extracted phase noise, as I stated before, and also this is a polarization fluctuation component. This can be accomplished by very simple digital signal processing. This is our secondary discovery. And so even, as you know, in the optical fiber transmission lines, frequently state of polarization changes. But we have to extract only the phase noise component from that. So by this technology, we can extract phase noise component, and this can be used to evaluate the performance of the system. Then, by using this technology, we have done long-haul experiments using the optical fiber and inline LBM optical fiber amplifier. And in this case, total length was 320 kilometers, and inline amplifier span was 80 kilometers. And this is a research purpose for we intentionally changed the optical output of the inline amplifier to be 0 dBm and plus 5 dBm. This is the result. Blue one is result for the fiber input power of 0 dBm, and the red one is fiber input power of plus 5 dBm. And this solid line is the measurement results, and this broken line shows theory. So you can see good agreement between measurement results and theory. And so next problem is how to apply this our new technology to actual WDM systems. This is very simple. This is a configuration of the WDM systems, as Mr. Saito stated, and simply we add new wavelengths to here. This is a continuous wave signal laser, and this is multiplex. And then at the receiving end, we apply delay interferometer system and the signal processing. So that can evaluate the system phase noise and SOP fluctuation. And especially in the fiber transmission line, it is known that the optical phase noise increases due to self-phase modulation. This is the nonlinear fiber effect, and XPM, cross-phase modulation, and also fiber four-way mixing. These are nonlinear phenomena, and this causes much problem to the transmission quality. So since this wavelength is transmitted with other transmission, data transmission wavelengths, this wavelength can measure the total phase noise increase affected by optical nonlinearity. So that will be helpful to evaluate the system performance of the WDM system. Yes, then I will switch to the high power consumption program. As Mr. Saito stated, in the digital signal processor of the coherent receiver, we consume much power, especially polarization, Dmax, and PMD compensation part. The tap coefficient is updated frequently for preparing the rapid SOP state of polarization changes. But usually, state of polarization change is very slow. But suddenly, it's a rare case, once in a day or once in a few days. So they consume much power here. So to solve the problem, we have invented this idea. Here, we tap the signal right here and apply delay interferometer system. And as I stated before, we can measure the state of polarization fluctuation speed by this DI system. So this information is introduced here. So if the very rapid polarization occurs, DI system detect, and this will change the update speed of the tap coefficient to be higher. But usually this can work in a slow speed. So this will reduce power consumption. So for this purpose, we use delay time difference. In the digital coherent receiver, dispersion compensation is also performed by FIR filters. It has a lot of memories, electrical memories. So it takes longer time, very long time, about several hundred nanoseconds. But DI systems is a photonic circuits. So delay time is very short, several tenths of a nanosecond. So using this time difference and tap the optical light signal light here, and we can notify this part that very rapid polarization fluctuation occurred to this part. But real data comes to here after that. So we can proactively change the tap coefficient update speed here using this optical technology. And of course, as I mentioned, that delay interferometer is useful, but also, as I stated before, commercially available technology, polarimeter. This is also optical circuits can be used to this idea. So we are now demonstrating in this area, exhibition area, the technology, as I stated, we can compare this delay interferometer system and a conventional polarimeter system by introducing rapid polarization fluctuation. So if you are interested in, please visit here. You are now here, and our booth is here. Thank you.
At last, I explain our future plan. We are considering incorporating the DI system into the WDM system. If the DI system is implemented to the WDM system, it will acquire the novel sensing technology. The DI system optimizes the power consumption of the transponder. By the way, WDM systems are also used in academic information networks. DI system will contribute to the development of academic information networks in the future. We, SoftBank, will realize a high-quality, low-power network. It will be an infrastructure adapted to the AI era. Thank you very much. Thank you for listening. Please make a question for us.
Okay, thank you. This very nice presentation and nice works. Did you have any idea or any plan to measure something like this, the noise and anything in among the network trend in the Asia Pacific, something like from the Japan to Indonesia to Hong Kong to Singapore to Indonesia, to know what is characteristic of the fiber itself in some maybe in submarine cable in some specific area in the metropolitan area, so we can know which one maybe have a trouble or something, because there is so many cable across the Asia that maybe when something like a earthquake and then the cable is disrupt, and then yeah, they have to find another way, another path. Maybe if you I mean the SoftBank or have some project or some idea to expand the measurement of the WDM, yeah, something. Thank you.
Thank you for question. 最初答えていいですかね。We SoftBank has a large, a long terrestrial network, but also we have the submarine network, you know. So we must pay attention both terrestrial network and submarine network. And SOP is mainly caused on the terrestrial network because this is caused by the vibration of the fiber. In the seabed, generally, a fiber is static, but if SOP is occurred, we must pay attention to the SOP also in the case of a submarine network. And the phase noise is occurred almost in the submarine network. In the submarine WDM system, they have very much power, and the causes a non-linear effect is known as it causes a very large phase noise. So this sensing technology is also important for submarine network you mentioned. Thank you.
Technically speaking, this technology can be applied also to the submarine networks. And as earthquake detection, distributed acoustic sensing, that is some kind of OTDR, optical time domain reflectometry technique, can also be used. In our Meiji University, we are also doing such a research.
Thank you very much for very informative presentation. And I'm so interested in the SoftBank's strategy as harmonizing with the its operator or the so-called mobile communication the business field. And I know the software bank also engaged with the AI RAN or the comes enhanced the edge based terrestrial networks. So my question is current your strategy towards those as wireless related as application by using those sensing based optical network. And in such a field, I believe you need a kind of some topology, network topology construction and configuration according considering about those like it's kind of such a business. And if you have some idea or some vision, please share with us.
Thank you for questioning to us. Yes, you're right. Do we have wireless system and wireless network? And today we talk about mainly about the optical network, but we have a wireless division and optical transmission division and several divisions. So we SoftBank should unite the collaborate the operation. So we have an operation center and operation center for optical network and operation center for wireless network. We should and they should collaborate. And this the result of this monitored result is gathered into the NOTE Cooperation Center, and we must discuss about dealing with gathered information. But this is a future discussion from now. Thank you.
Thank you.
Thank you for your interesting talk. I have one technical question. Is it a research phase, right?
Yes, I talk about phase noise.
Yeah. So my question is, what is the problems from research area, research phase to commercial products?
This shows the effect of phase noise, and yellow part means phase noise. And if phase noise become large, a bit the distance of point is closer, so error is occurred. In the optical transmission, error should not occur, but if phase noise become large, error has occurred. It is very critical to optical network. So we must check where is the source of phase noise, and we must pay attention to the source of phase noise.
Okay, thank you.
Oh yeah, sorry. It was a wonderful presentation. Thank you. Just a quick question. Can this also be adapted to pluggables, or is it just for typical DWDM networks? I'm talking maybe DWDM over IP in coherent pluggables. So can this also be adopted for those pluggables?
Yes, in this today's presentation, I wrote only the transponder case, but as you mentioned, recently a coherent receiver, coherent transceiver becomes a very small form factor like QSFP-DD or OSFP, yes, as you mentioned. And this DI system technology can be applied to the coherent transceiver, small size transceiver is also applicable. Any other question? Okay. Okay, thank you very much.
Thank you very much.